Hey friends, we are still in chapter 9 and we're looking at section 9.5, scientific notation. And the cool thing is that scientific notation is going to be a review, which is fine. So this shouldn't be too hard, nor should the lesson take too long. Let's get started. We only have 2 vocabulary words, and as I said before, this should be review. So standard form is when a number is written, let's not use that, when a number is written in a regular way. So standard form would look like the number 3, the number 3,407. Standard form, you can also have particularly small numbers when we write them in standard form, lots of zeros, 4, 7, something like that. Or we could have standard form where we're dealing with really large numbers, right? Something like that. Okay, so all of these numbers are written in standard form, but if I were to write each of these numbers in scientific notation is the process of writing numbers in a form that is going to be really convenient for calculation. And so we write numbers such that we're multiplying a whole number, well, not necessarily a whole number, we're multiplying a number that is somewhere between 1 and 10, right? So it's less than 10, but it can be equal to 1. So some number x is going to be between either equal to 1 or greater than 1, but definitely less than 10. So it's going to be close to a single digit as possible, but we can have decimals. And we're going to multiply it by 10 to a power. Okay, and that's basically what scientific notation is. So I'm going to circle this in red and write each of these in scientific notation. So how would I write 3 in scientific notation? It would be 3 times 10 to the 0 power, because 10 to the 0 power is 1, and 3 times 10 to the 0 power is 1. That's not particularly convenient, I know. Let's write this in scientific notation. So if I'm writing this value, I'd write 3.407. Notice I used this first number. I wanted to make sure that the way I wrote it was such that such that the number was between 1 and 10. And now I'm going to compensate for what I did here by multiplying this number by 10 to a power. Well, very simply, in a sense, I took the decimal point and I moved it 1, 2, 3 spaces to the left. So that means I made it smaller. In order to, I guess, reconstitute the number, I'm going to have to multiply it by a bigger number. So that's going to be 10 to the 3rd power. So it does correspond with the number of places we move the decimal point. Let's try this next number. So I have 1.4, doing this one here, 1.435678. Now technically this is a lot of digits to write, and oftentimes scientific notation, when you have things like this, you will be asked only to write 2 or 3 numbers after the decimal point. However, I'm going to write it all so I can write exactly what I am exactly the value that is here. And so how many places did I move my decimal? 1, 2, 3, 4, 5, 6. 6 places. So this is going to be times 10 to the 6. So what this does, I'll do this last one here. What this does is this gives us an idea of the magnitude of our answer. So now notice I'm moving it to the right, so I'm making this number that was really tiny kind of bigger. So to compensate for making it bigger, I'm going to multiply it by something small. Now it sounds crazy, but hopefully it makes sense. So 1, 2, 3, 4. I'm going to raise that to the negative 4th power because I moved it to the right. This sort of sound familiar? I hope so. I hope you remember it from last year. Let's take a look at the first example. Okay, so for this example, what we're doing is we're going to express each number in standard form. So if we express a number in standard form, basically what we're going to do is take this scientific notation number. So I realize that I've got 2 point nothing times 10 to the 3rd. And what I'm doing is I'm going to use this number, the exponent, to figure out how many spaces to the right I'm going to move my decimal. 1, 2, 3. So this number, I'm going to fill those spaces with zeros, and so this number is equal to 2,000 when I write it in standard form. When I have a positive exponent, I'm moving to the right. When I have a negative exponent, I'll be moving to the left, as we'll see in part C. Let's look at this next example. So I start off with 6.8. I'm going to move it 5 places as my exponent indicates to the right. So 1, 2, 3, 4, and 5. I'm going to fill, in a sense, all these places that I've created, and I see that my answer is 680,000. So when I see 10 to the 5th power, I know that I am in the hundred thousands place. Does that make sense? All right, hopefully it does. Here, we have a different situation. We're dealing with a negative exponent. So as I mentioned before, negative exponent, we don't move to the right as we did in these two examples. We're going to actually move to the left. So here we have 3.25. It's not, there we go. 3.25, and now, let me use red, I'm going to move 1, 2, 3, and 4. Four spaces, and I'm going to fill those spaces with zeros, and I'm going to emphasize the fact that my decimal point is now here. So this answer is going to look like this. Of course, we can put a 0 in the front there. All right, so that's it for example 1. Let's take a look at example 2. Here in example 2, we're going to express numbers now in scientific notation. We had a good practice with that when we looked at the vocabulary. Remember the key here. You're going to multiply a number. Let's say this number x is going to be somewhere between 1. It can equal 1, but it has to be equal to or greater than 1, but certainly less than 10. So we're going to multiply that number. This is a times sign and not an x here. Let me make it a little bit darker. Then you're going to multiply by 10 to a specific power, depending on how far you move the decimal place over. So if we're going to move the decimal place over to the right, over to the left in this case, so we're taking a large number, we're going to make it smaller so it could fit scientific notation model. That means I'm going to be multiplying by 10 to a positive power. In this example C, notice I'm going to have to move my decimal place over to the right, making a smaller number larger. I'm going to have to compensate by multiplying by 10 to a negative power. Let's go ahead and get started. So here, my decimal place is here. I'm counting back 1, 2, 3, 4, 5, 6. So my answer will be 4 times 10 to the positive 6th power. Remember, it's positive in this case because I'm making a large number small. I need to compensate by multiplying by a big number. The next thing I need to look at is this example here. I have 1, 2, 3 places that I need to move that decimal point in order for things to work out or be in this form that I like, where the first number that I'm multiplying by is between 1 and 10. I'm going to multiply that by 10 to the, since I moved it back 3 spaces, 10 to the positive 3rd power. Finally here, I'm going to move this to the right, right? I'm going to move it to the right 2 spaces. So I have 7.2 times 10 to the negative 2nd power because I made a small number larger and I need to compensate by multiplying by a tiny number. Does that make sense? Let's go on to the next example. All right, here we are in example 3, and we're looking at ants in the rainforest. So, in the rainforest, scientists estimate that there are 3.5 times 10 to the 6 ants per acre. Real quick, 10 to the 6 should already alert you to the idea of a million. So there's 3.5 million ants per acre in the Amazon rainforest. If the Amazon rainforest covers approximately 1 billion acres, find the total number of ants. And we're going to write our answer in scientific notation. Well, let's think about what we have. First of all, I have 3.5 times 10 to the 6th power, or times 10 to the 6 ants per acre. How many acres do I have? I have 1 billion acres. So I can write 1 billion as, well, 1, right? 1 billion times 10 to the, do you know what the power would be when we're dealing with billions? How many zeros are there? 9. Good. So I've got times 10 to the 9. Now this doesn't look great. However, what this does give me the power to do is use my exponential powers, right? Here I have 2 numbers with the same base. So I've got 3.5 times 1, which gives me 3.5. So I can multiply those guys together. And then 10 to the 6 times 10 to the 9th is pretty easy. That's just going to be 10 to the 15th because I'm adding those exponents together. So this would be the number of ants that are estimated in the Amazon rainforest. Does anybody know what the 15th power would be? Tell me in class if you know what the 15th power would be in terms of place. Would it be billions? No, we already know that's 9 trillions. Would it be quadrillions? Would it be, talk to me in class. You'll tell me. All right, let's look at the next example. Example 4, Earth science. The table shows different geological time periods ordered, and we're going to order the time periods from oldest to youngest. All right, so let's see if we can get ourselves started. So we see the Jurassic time period was this many years ago. The Silurian time period was this many years ago. Tertiary Tertiary time period was this year, and the Triassic was this many years ago. So we want to go from oldest to youngest. So if we're going to start with the oldest, which one would be the oldest here? Which one would be the most number of years ago? We see that these guys are all 10 to the 8th, whereas 10 to the 7th is more recent, it's less years. So we know that this is the youngest. So I'm going to put that at the bottom. 6.64 times 10 to the 7th, and that's the tertiary. All right, so now I got the youngest. Let's get that out of the way. Let's see which one would be the next youngest. Well, since these all have are to the power of 8, we need to now look at this number here to kind of determine which one is the next youngest, the least furthest away, and that would be the Jurassic, because 2.08 is smaller than each of these numbers. So I'll put this down, and then I'm going to put down Jurassic. And I think you guys can follow along and do the other ones pretty simply. 2.45 for the Triassic period, and I'll put that here. And finally, we have the Silurian period, which is the oldest, which is 4.3 times 10 to the 8th years ago. All right, with that in mind, I'm going to ask you guys to have a very good day. Let me know if you have any questions. I look forward to talking to you in class, and I'll see you next time. Take care. Bye-bye.